There we go. I had forgot to turn the wireless mic on, so if that's not on, I just go. It's no good. I will begin with a word of prayer. Dear Father, we thank you for this day. Thank you for these students, and I just ask you to bless this class, Lord. In your name I pray. Amen. So, today I just want to try to take a step back and kind of collect our thoughts about what is homotopy, what's it for, and if I can, try to say, just collect some of the big picture comments in this Yannick's Topology book, which just has some great discussions. I will attempt to mirror them in this class. We'll see what happens. Pick up in chapter 5 of this, where he talks about homotopy. And so the notion of homotopy he talks about here is a little bit more general than that of curves, all right? So like here, I'll start with this definition. Well, really notation, he calls it. He says if x and y are topological spaces, then he's going to use the notation bracket x comma y to denote the set of equivalence classes of homotopic maps from x to y. He says, so basically the idea is, looking at, can you morph one map into another, all right? We've focused most of our attention on, homotopy of curves, but the concept is more general, right? The larger idea is, can you morph one map into another through some continuous family of maps, right? And this leads to the notion in his section 2 of homotopy equivalence. All right, what's homotopy equivalence? All right. Well, let's write that down here. So he says, a continuous map f from x to y, all right, is called a homotopy equivalence between x and y if it possesses a quote-unquote homotopy inverse. What's that? What would it mean to have a homotopy inverse? Well, what that means is that there exists another continuous map, G, from y to x, all right, with G composed with F, not equal to the identity on X, but homotopic to the identity map on X, and F composed with G, not equal to the identity necessarily on Y, but homotopic to the identity on Y. So it has an inverse. Basically, it's an invertible map up the homotopy. Right? This is a homotopy inverse. All right. In this case, he says F and G are homotopy equivalences. When we then say that F and G are homotopy equivalences inverse to each other, and we call the spaces X and Y homotopy equivalent. All right? So with this setup, we can define, I don't think we did this before, did we? I mean, you mentioned it, I think. We talked a little bit about it, but I never wrote anything on the board. It's been brought up by you guys, not me, up to this point. But with this setup, we can define contractible in a different way. What was contractible? What does it mean for X to be contractible? Well, here it is. A topological space is called contractible if it is equivalent to a space with one point. And of course, we're talking about homotopy equivalence, right? All right. And then we define retract. All right, so retract or deformation retract. What are these ideas? It says let X be a topological space. All right. And A a subset of X. Then A is a retract of X if there exists a retraction rho. That means a mapping from X to A such that what? So it has to be a continuous map such that rho restricted to A is just the identity on A. All right? Furthermore, he says, now if rho is also homotopic to the identity as a map from X into X, then rho is called a deformation retraction, and A is correspondingly a deformation retract. So what's the next here? What did I just say? my memory's horrible. Uh-huh. And then finally, he's got the strong what's a strong deformation retract? What's that? What was that? If the homotopy between rho and the identity can be chosen such that all of the points of A are kept fixed in its course of it, then rho is called a strong deformation retraction, and A is a strong deformation retract of X. All right, I'm not going to write that down. It's on page 62 of Yannick, all right? Now, one of the things that sold me on this book being worth you guys looking at is he now has, he has this wonderful description of how we actually think about deformation retractions in practice, right? He sort of sketches a strategy here in the next two paragraphs. He's like, whenever possible, one tries to avoid, actually looking for specific maps F and G which are homotopic, right? And writing that all in detail. Instead, what you want to do is try to, make identifications of homotopy equivalent spaces as some sort of composition series where each step takes you from one space, which is homotopic, to the last, which is homotopic to the last. And so he has some pictures of these. Like I'll foolishly attempt a couple of them. So his example 1 in terms of like deformation retractions. He says the origin is a strong deformation retract of Rn. And I think he just has essentially the picture for dn. So here's a picture of dn, right? And here's a picture of the actual retraction. You just shrink this is basically just literally what you kind of imagine. You contract the space to that central point. That is the deformation retraction. He says, but this means that A cross 0, where A is any topological space, is a strong deformation retract of A cross Rn or A cross Dn. He says A is retract of A cross, I'll use Dn because it's easier to picture. So what's a picture of A? What is that? How do you picture a Cartesian product of A and Dn? A is just any topological space. Any old topological space. So yeah. Well, I'm going to draw a picture that I can draw, so I'll picture N as 2. 62 or 63. Yeah, I mean, I'll be lazy and do it like he does. He just draws A as like a, he draws A like that. And so if that's A, then you can kind of, in your mind's eye, picture A cross Dn. And more generally speaking, if you think about a Cartesian product of, say, X with A, or A with X, what is, more generically speaking, if you just have a Cartesian product with X, what that is, you can think of A as whatever, and you can think about it as sort of just, if X is like a line segment, it's like gluing a line segment at each point. I mean, that's what it is. You're just gluing a copy of X at each point along A. This is the way to envision a Cartesian product. It's a very heuristic picture I'm drawing. I mean, A could be infinite dimensional, whatever. So here, this is like, but this is a slightly different picture. This is A. Dn, he pictures as, like a cert like this. So this would be some sort of, like a tube in my picture. And what he says is that A is the retract of A cross Dn, and the retraction, you can kind of envision it. You just duplicate this Dn contraction at each slice. You just kind of imagine. It's the n ball. It's the set of points less than or equal to distance 1 in Rn. So it could be like for D2 would just be the unit disk. Yeah. The solid sphere, but yeah. So you could basically contract at along each point in A, you can just contract the dn down to a point. Is the Cartesian product of contractible spaces contractible? I believe so. He says, okay, so in particular, the solid torus, which is, we take A equal to S1 and, D2, like S1 cross D2, that's just a donut. That's homotopy equivalent to the circle. Basically, you can take the donut and shrink it to its center circle. And that's a homotopy equivalence. And then he has some more exotic examples in the next 2 pages. I'm gonna go on. So this is, quite a beautiful idea. I was hoping King would show up. Kind of buying time at the moment. I'm going to stop buying time and go on. So, oh well. I guess he can watch it later, but I don't know. All right. So these we don't need anymore. Mostly I'm going back over this just to just sort of get it back in our head again as we have the discussion that goes on. I just wanted to have a little bit of this idea for the upcoming discussion. And so section 4 is on categories. So I would be remiss if I didn't say at least a couple words on category theory in here. Not that I'll say anything, really hardly anything deep at all, just the most rudimentary things I'll tell you. All right, so first of all, what's the definition? What's the deal here? And so the definition here is of categories. So my goal at the moment is to define categories and then go on and define what's a functor and try to explain to you what that has to do with what we're doing. So categories. A category and we'll call it, I'll call it C, consists of the following data. Okay, so what's the data? Part A class of objects, which we'll call obc. These are the objects of the category. A class of mathematical objects, these are called the objects of the category, part A. Part B, a set of morphisms. All right. So in particular, more xy for each pair of objects. All right, so a set of morphisms for each set of objects. And he says where the morphisms from x to y and the morphisms from x prime to y prime are disjoint if the pairs x, y, and x prime, y prime are distinct. So the elements of more x, y are called the morphisms of x into y. And then he says some kind of cagey things about using function notation even when they're not functions. So morphisms are often functions, but they don't have to be. I'll give a specific example of when they're not, a specific non-function example in just a minute, okay? So I'll clarify more what morphisms are in our examples, all right? And then C, a law of composition for the morphisms. So for each triple of objects, x, y, z, we write the law of composition writing fg maps to g, good grief, yeah, g composed with f, corresponding the notation, I don't know what I'm writing now, down right now. what I'm writing at the moment doesn't make a bit of sense to me, guys. But I think it's clarified in the equation, which is a little bit below. I mean, this just seems like word soup to me at the moment. Law of composition for morphisms for each triple of objects x, y, z, writing f comma g is g composed with f. A law of composition. I missed. Let me put it in a different color. In fairness to him, yeah, I'm supposed to write more x, y cross more yz to more xz. Help me out. I've already forgotten it. And that's for each triple of objects. So, in other words, you have a function going from, not necessarily a function, a morphism, going from x to y, and then a morphism from y to z. What's the law of composition? I guess the law of composition is that you can compose them, right? And that what? Right. The point is that this morphism, that is an element of what? More xz, right? That's the law of composition. It says the composition of morphisms in the natural sense is, again, a morphism, right? But that's not all. You got these objects, you got these morphisms. They also have to satisfy a couple axioms. What are the axioms for a category here? All right, so the axioms. Axiom 1 is that associativity. Right? So if we have morphisms, and we'll use function, I mean, well, just to keep, this is, again, for morphisms. I'm not saying that these are functions. They may be, they may not be. For morphisms, f, g, and h, from objects x to y to z to u. All right? We have that h composed with g composed with f is h composed with g composed with f. Like so, all right? And axiom 2, what's axiom 2? Identity. What would that mean? for every object x, right? For every object x, what should there be? Yeah, there exists an identity morphism. And we're talking about, of course, the morphisms from x to x. There's an identity morphism in the morphisms from x to x with the property, and, well, what does he mean by that, right? Meaning that 1x composed with f is f, and g composed with 1x is equal to g again for all morphisms f from y to x and g from x to z. All right, so one of the things that's driven me nuts as I've heard people talk about this in like a hurry and without, you know, and I'm probably guilty of this too, is a lot of times you get the idea that the morphisms are functions. Or you get you're left with the question, well, what do you mean it's not a function? Like, is there even an example of that? So I think I've been guilty of both things, of saying that morphisms have to be functions and or not giving examples of how, not giving an example where it's not actually just functions. So I'm going to continue in that vagary for just a minute or two, because I think it's important to look at examples where the morphisms are functions to start with, because that's kind of the most natural context of this definition is in the case that the objects are an object that you're familiar with, some sort of set that you're familiar with, or class of sets, and the morphisms are actually functions from the set to the set that typically satisfy some particular characteristic, and the law of composition for the morphisms is literally composition of functions. And we know composition of functions satisfies these axioms. Axiom 1 and axiom 2 are true for functions on sets. There's always the identity function on a set. You can define it. It's not a big deal, right? Well, it's only as big a deal as you are careful about set theory, right? So for me, it's not a big deal at all because I'm pretty careless. Disclaimer, these things are all done more carefully by people who know much more than I do about them. And these things are on the internet if you're interested. I think my previous student, Nathan Bedell, was watching these casters videos, I think it is. Is that right? I don't know. There's a whole series of category theory done really, really carefully. Okay, anyway, let's examples before I blather on too long. So example 1, this one's kind of plain Jane, but you could just look at M, category M of sets. Let your objects be sets. And morphisms, what would the morphisms be? Just maps? Just functions on sets. This is a category. Example 2. The topological category. So what's the topological category? What's the and he uses top for this. All right. What are the objects in this case? What are the morphisms? Yep, topological spaces. And continuous maps. He points out that you could also define another category of topology. You could define a very related category to top, all right, where you use the same set of objects, topological spaces, but instead of looking at continuous map, just look at maps. That would also be a category. You could enlarge the set of morphisms, drop the requirement of continuity. It would still be, that would be a different category, right? Example 3, category of groups. All right, what's his notation? Does he have a notation? Yeah, he has notation. No. I'm going to call it group. There. That's my notation for it. What are the objects? What are the morphisms? Groups and indeed group homomorphisms. It means that it preserves, if we have psi going from, say, G with operation star to H with operation wedge, then psi of x star y is equal to psi of x wedge psi of y. It preserves the group operation, whatever that group operation is. Oftentimes we look at a homomorphism which takes like composition of linear like composition of linear transformations to multiplication of matrices, for example, is a common homomorphism between the group of functions under composition and the group of matrices under multiplication, if we're looking at
So most broadly constructed is a set with permissible transformation?
a group is a set with an operation which satisfies the axioms for a group, namely that there exists an identity, that the group operation is associative, the group operation, of course, is a binary operation, and the closure under inverse, the axioms of a group, yeah. There is also a category of vector spaces. So for K vector spaces, 5 category of K vector spaces, and then, this example. Example 5 is topological vector spaces over K. What's the distinction there? So in 4, K vector spaces is the objects are K vector spaces. K is a field, okay? So K is probably, well, for my taste, K is R or C. And the thing is, for the category of vector spaces, the morphisms are simply K linear maps. What are the morphisms for topological vector spaces over K? Well, first of all, the objects are topological vector spaces, right? Which means it's a vector space with a topology. and the morphisms are continuous linear maps. In the infinite dimensional case, you can have more linear maps than you have continuous linear maps. There are unbounded linear maps. When you study functional analysis, you'll learn about the distinction between continuous linear maps and discontinuous linear maps. That's kind of weird to your current experience, right? Finite dimensional linear algebra, every linear map is represented by multiplication by a matrix. If there's a formula like that, it's continuous. You can bound the map using the entries in the matrix, blah, 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 blah. Okay.
I still don't know what objects and morphisms are.
Right. So that's the thing, is the objects are the set of spaces we're looking at, and the morphisms are the allowed transformations on that kind of space. That's a good intuition for most of the examples. But the idea of category has been defined more abstractly than that. That's usually the case, but not always. Right. His example 6 is an important example. Let me try to get through this example because I do want to make sure I don't run out of time here. The differential topological category. Or as he calls it, diff top. All right. So the objects here are, let's say, differentiable manifolds. I might say smooth manifolds on a different day, and I might say this is the category of smooth topological spaces in the sense that they're well, anyway, we haven't defined manifold carefully anyway, but and the morphism in this case would be differentiable maps. Well, a manifold is depends on who you are, but a lot of people would define a manifold to be a relatively nice topological space, which also comes with it a maximal atlas, an atlas of charts which cover the manifold, such that these charts put the manifold in local one-to-one correspondence with Rn. And really, there exist local homeomorphisms to Rn. More than that, though, any two overlapping charts in the atlas are compatible. This means that if you track through the coordinate charts back down to the corresponding map from Rn to Rn, it is differentiable in the sense of advanced calculus, in the sense that it has an invertible Jacobian, that you can calculate partial derivatives of the transition functions. But a more glib description of what a differentiable manifold is just it's a curved space where you can do calculus.
Is that the main application of advanced calculus?
Advanced calculus is trying to build towards being able to do calculations on manifolds, yeah. That's one of my main goals in there. But that's not, it leads to that. It's not that. Yeah. He also gives the example of a vector bundle, and a category of vector bundles, and a category of n-dimensional vector bundles. This isn't going to help you anymore. You're still like, so what is it, right? His example 9, I don't care for, but his example 9, I'll let you read his example. I'll say it in words, I'm going to write it down. Example 9 says, let G be a group. Take only one object in the set of objects to be the identity. And so if there's only one object, you're only obligated to talk about morphisms from the object to the object. And he says let the morphism from the object, morphism from E to E just be the group. If you sort through the definition here, you'll see that you've satisfied the axioms somewhat vacuously, but there it is. And then the composition is literally group multiplication. So example 9 shows you that the definition of category is much more robust than the basic interpretation in terms of it's a set of objects and the allowed transformations on those objects. All right? But example 10 is important to us because example 10 is the homotopy category. The homotopy category. And in this case, the objects, well, again, topological spaces. But what are the morphisms? He says the morphisms are the homotopy classes of continuous maps. It's what I started today with. That's the morphisms, homotopy classes of continuous map. And composition is defined via the, homotopy class represented by G, composed with homotopy class represented by F. Well, it's just the usual homotopy product that we've grown used to, right? I think. Maybe not. But there it is. He says, after the definition examples, no, I don't want to read that. All right. So the larger point is the notion of a category, it transcends any particular discussion we've had in different courses. If you go back and look at all the courses you've had, almost every course was about a particular category and studying aspects of the morphisms in that context, right? But you can also see that there's things that are common to all of the different classes you've had. Like if you take a good look at certain theorems we discussed in linear algebra, you can see that that same theorem was present in group theory. And if you were to study Lie algebras or other things, you'd see this again and again, that certain theorems are kind of, well, they're not about really the particular category that you're looking at. It could be that they're actually about the category of sets. And so any category which, if you forget the structure that you're looking at and strip away and go back to the underlying category of sets that you have there, if the theorem is true for the category of sets, it's going to be true for another category, which if you apply the quote-unquote forgetful functor to, you're back to the category of sets. Now, what's a functor is the next question. Yeah, I have nothing to say about that. Right. Exactly, because you can't make a you can't really explain that here without getting into a discussion of the foundation of set theory, which we're not going to do. So.
It is important just in that you can also talk about the category of categories.
Uh-huh.
You can't talk about the category of large categories. Only talk about the category of small.
Well, I will let you guys talk about that because I have nothing to offer in this regard. We're talking. The question has been raised about the distinction between the set of sets versus the class of classes, and why is it that relabeling things by class rather than set avoids the Russell's paradox, right? The barber cutting his own hair and blah 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 blah. And yeah. Okay. I'm not dismissing it. I'm just dismissing it. So, definition. I don't have anything to say, guys. I'm sorry. Covariant
Something to
functor.
say, something to say.
Covariant, yeah. The thing I have to say is I don't have anything to say, so there you go. So if you look at the set of all empty state, no, see, covariant functor. Covariant functor. What's a covariant functor? If you have categories, C1 and C2 categories, all right? And the functor is something that goes from category 1 to category 2, all right? And it associates to each object. So it's going to take x in category 1, object category, x in category 1. Oh, I shouldn't say element of that, should I? That's not how that works. Sorry, too much topology. Object x of category 1. A category is not a collection of objects, right? A category is a collection of objects and a collection of morphisms, which satisfy certain axioms. In contrast, a topology is a collection of subsets of a set, right? A category is more carefully defined than that. It's morphisms and objects, right? Anyway, object x of C1 is mapped to, by the functor, f of x and object in C2, right? Is that right? But it's more than that. Also, if we have a morphism from, say, x to y for category 1, then f of v is going to give you what? A corresponding morphism from what to what? A corresponding morphism from the object which corresponds to x under the functor, I suppose, to the object which corresponds to y under the functor. So this functor, it transfers over both objects and morphisms, both. Yeah? Have I butchered the definition? Okay. And more than this, the functor has to do a couple things. One thing is it has to send the identity morphism to the identity morphism appropriately. And two, and again, we're covariant functor, it has to map the composition of morphisms to the composition of corresponding morphisms. All right. This is a functor. It maps from one category to another. This is a covariant functor because it preserves the order of composition. There's also contravariant functors. Contravariant functors mess up the order of the composition. So the definition, I won't even write it out, but for contravariant functor, this here gets flippity-floppitied. Like the contravariant functor, like that. All right? Now, and then he says it doesn't, he says, in some sense, even working with contravariant functors is just a convenience of notation, because you could look at the dual category to a given category and convert. You could trade your contravariant functor for a covariant functor if you were so inclined. Appropriate notion of dualism. He then makes a reference to dual vector spaces in linear algebra, which will not be helpful to any of you. And then goes on to talk about the central question, the reason I'm even having this discussion: what is algebraic topology? Right? So what is algebraic topology? Have we seen a functor? Right? So he describes then that algebraic topology, of course, is the study of calculation of topological invariants. To each topological space, we try to associate some number, right? Perhaps like the Euler number or the Betti numbers.
The Betti number is not a constant.
Right. Well.
I mean, you can have a function for it on a space.
Well. Well, let me say it this way. He says, from a modern point of view, algebraic topology, I'm on page 72. From a modern point of view, algebraic topology is the finding, calculation, and application of functors from the geometric categories, topological or differential topology, into algebraic categories, groups or rings and so forth. All right? So I spent a day trying to describe to you guys the homology functor. All right? The simplicial homology functor. What we do there is we take, he says, the k-dimensional homology, let me write it down here. He says HK is from, top to what do we do with homology? We take a topological space and we associate it to A, for the one I talked about, in our vector space, right? And I championed the idea that it allows us to calculate specific numbers that we can attach to the topological space, right? And if you have two different topological spaces and these numbers you calculate are distinct for different topological spaces, then that speaks to them not being homeomorphic, right? And that is true, and that is the most classic and not most interesting, but it's a classical application going back to Euler and like Euler characteristic, as he explains in here. But the point he makes on page 73 is deep and interesting, which is that the functor not only gives you like a way of attaching numbers to the topological spaces, it also says something about maps between spaces and the way maps have to interact. So let me just I'll probably end here, but this is a pretty good place to end. So he says the functors not only give information, I'm on page 73, information about the geometric objects, but also about the geometrical morphisms. And so here's his example, which I think we've talked about before, but it's nice to calculate here afresh. So he's like, here's the question that he's going to beg. Suppose we have a surjective map from X to Y about which we already know, for instance, that it's not injective, all right? So here's a kind of a rough picture of the situation. Here's Y, all right? And then up above here, there's some sort of space. And here he has the so-called image of a section. And, okay, so there's some projection map pi going down here. The question is, does there exist sigma? All right. That goes the other way back up. Now each one of these, so if this point is like y, all right, then up here, this over y, we have the fiber, the pi fiber over y, if you like. So like this guy up here would be pi inverse of y, all right? And, all right. So here's the question that he specifically raises. Generally speaking, the question is to decide whether or not a morphism pi from x to y has a right inverse. So does there exist, given pi is a surjection from x to y. So x is up here, guys. Y is down here, and the picture is trying to give you the idea that it's a surjection, but it's not an injection because the fibers are, not just singletons, the pi. Does there exist a sigma going from y back up to x, all right, such that pi composed with sigma is equal to the identity on y? If it's possible, this is called a right inverse. In other words, we're asking the question, does there exist a right inverse to pi? You see why that's called a right inverse, right? Okay. Now he gets more specific, all right? He's like, okay, let's take, for instance, the continuous map pi from S3, the 3-sphere, to the 2-sphere. All right? Consider the surjection from the 3-sphere to the 2-sphere. Can this have a section? Can this have a right inverse? Does there exist a sigma from S2 to S3? Right? Such that the composition of pi and sigma is the identity. Is this possible? Well, if there was, then we'd have the following picture. We'd have S2 maps under sigma to S3, right? Which maps under the surjection pi to S2. S2 is the 2-sphere, S3 is the 3-sphere. S2 is the one you can visualize. S3 is the one that only like a couple people can visualize. So, the question is, so if there was a right inverse, we'd have that, how's it go? Sigma composed with pi would be the identity, right? But we have a functor, which the homology functor is a covariant functor, I believe. So in particular, the homology says, well, it's not sigma anymore, right? I better kick it up a notch here. I'm going to get in trouble. All right. I got to finish this thought. So the homology functor says that there exists a diagram like that. And then that is of course, that's a whole family of vector spaces, an infinite family, each one for each k. But let's look at the k that we know something about, right? Like the second homology. We calculated that, let's see here, H2, S2 is Z. Oh, man. Oh, phooey.